Hello, and welcome to this presentation on the polarization experiment. My name is Daniel, and also presenting will be Zach, Julia, and Danny. This is the poster for our experiment, which we will go into more detail on in this presentation.
Composite materials are often used in radome construction. The composite material properties and the radome geometry influence antenna radiation characteristics. Composite material is generally defined as a material that consists of two or more dissimilar materials. Composite lamina is a single layer of composite material, whereas a composite laminate is an assembly of composite lamina stacked together. The top figure shows a composite radome on an aircraft. The middle figure shows a combination of a fiber and a matrix to form a composite material. The bottom left figure shows a laminate construction consisting of three separate laminas stacked together, and the right figure shows a sandwich structure, which is a commonly used structure for radomes.
Waves are polarized, which means they have a preferential alignment of the electric field as it propagates and interacts with matter. For the purpose of this presentation and for this experiment, we'll only be dealing with linear polarization. The polarization of a wave affects how it transmits, reflects, scatters, and diffracts, which has all sorts of impacts on RF performance. A polarizer will block waves that are orthogonally polarized relative to the polarizer, while not blocking waves that are polarized parallel relative to the polarizer. As seen in the figure to the right here, we have TE polarization and TM polarization. As the wave, which is a combination of the two, passes through the polarizer, the TM polarization is blocked, whereas the TE polarization is allowed through. The fibers of a composite used to construct a radome could act as a polarizer. So the purpose of this experiment is to demonstrate the function of a polarizer and then to explore the impact that composites can have on polarization and how that can affect the wave propagation. To simulate this experiment, we used computational electromagnetics, specifically the finite difference time domain. Finite difference time domain directly solves Maxwell's curl equations to create update equations that are, as the name would suggest, finite and in the time domain. This, coupled with the Yee algorithm, allows you to step through time and space, constantly solving for and updating the electric and magnetic fields in the domain space. First, we developed a 1D program, and then we developed a 2D program for both one for the TE polarization and one for the TM polarization. Once we had this, we were able to define the domain space and the material parameters so that we could simulate the experiment.
DTD does not do a good job of interacting with curved edges, so we made our circles out of lots of tiny squares. In order to do this, first we tell the program roughly how big we want our grid size to be and how big of a space we want it to be in. Then the program will take the space of the grid that we gave it, split it up into quarters until it gets roughly the grid size we wanted. Afterwards, it will make one circle of radius x by throwing out every point that is farther than x from 0, 0. The remaining points can be thought of as one circle. And we can use those remaining points to shift the circle left or right.
These are the results of the same experimental setup, but with a TE polarization and a TM polarization. The TE polarization, because its electric field is parallel to the rods, the energy is able to pass through that grating and is able to reach the other antenna, whereas for the TM polarization, the electric field is perpendicular to the rods, and you can tell that most of the energy is reflected back and not allowed to pass through the rods.
Grid, we have three parameters: permittivity, permeability, and conductivity. Permittivity is related to how much of the electric field that is stored, while permeability is related to how much of the magnetic field that is stored. Meanwhile, conductivity determines how much of the electric wave will be reflected back. Here, we have different spacings of the metal rods. The ones with smaller spacing have more materials, and as you can see, are sending more of the wave back. Here, everything else is the same as free space for our rods, except for the permittivity. The higher the permittivity of our rods, the more the rods are mismatched and cause reflection. Rods that are orthogonal to the polarization direction will block the polarization. When spacing the rods out, the further they are spaced out, the less material getting in the way of the wave, causing less reflection back. Different materials have different permittivity, permeability, and conductivity. As such, they will reflect the wave back differently.
Future work on this project includes simulating the experiment in a 3D FDTD environment where both polarizations can be present at the same time, as well as confirming results in the lab. This would include building a low noise testing environment, which would use Absorber as seen in the lower right.
In order to experimentally validate our models, we designed and 3D printed a polarization rig to hold common RF or electromagnetic materials. Using this adaptable rig, our goal was to quantitatively measure the influence of material selection, spacing, and orientation on polarization. The rig was designed to hold different material rods, such as copper, glass, and carbon rods shown in these images. Future experimental work will entail testing polarization at variable frequencies, rotating the entire configuration to understand influence of orientation, and comparing polarization properties of unidirectional composite material to those of woven material or stacked laminates. Our polarization team would like to thank Dr. Bradley Davis and Jacob Vire for their continued support and guidance on this project. If you have any questions, please email any of the below contacts. Thank you.